Welcome to Math with Professor V. In this video, I'll be solving the final exam that I gave to my Calculus 2 class, spring 2024. I'm just going to jump right in, solve the problems, talk you through it a little bit, but if you need a more in-depth video lecture or review of the concepts, then I have linked in the description the Calculus 2 video lectures playlist. And so just go through that and that'll have every single lesson that's referenced throughout this video. Okay, get comfy and enjoy. It might take a little while. So first question was, use the shell method to find the volume of the solid generated by revolving the region bounded by the given curves and lines about the x-axis. You must include a clearly labeled sketch of the region, the solid, and a typical shell. And I am aware of the fact that at most colleges, this topic is actually covered in Calculus 1, but for some reason where I work, they put it in Calc 2. So here we go. First things first, we need to draw a graph. And in order to do that accurately, we need to find the intersection of these two curves. So let's go ahead, solve for the intersection. I'm going to set x equals 8 minus y squared equal to y squared. And I already know those are both parabolas, right, that are opening in the x direction, one in the positive x direction, one in the negative x direction. So it's going to look kind of like an ellipse. We have 8 equals 2y squared. So y squared is 4. That gives us y is plus or minus 2. And then from there, I can just go back and say, okay, if y is plus or minus 2, x is going to be 4. So that's where the curves intersect. And then all of the action is really in quadrants 1 and 4 because we're revolving about the x-axis. So that's where I'm going to put my axes. I'm not going to put all 4 quadrants evenly. Nothing interesting is happening over in 2 and 3. Here's x, here's y. They intersect at 4, 2 and 4, negative 2. But then also I'm noticing here 8 minus y squared. If I substitute in 0 for y, x is 8. That's the vertex of that parabola. So I'm going to go all the way out to 8. 5, 6, 7, 8. Okay. So this parabola goes through 8, 0. X equals y squared. That just goes through 0, 0. And then here we have their intersection, 4, 2, 4, negative 2. So let me draw x equals y squared. And then 8 minus y squared, that's over here. And then it's opening up negative direction. Okay, good. And then we're spinning it around, oh, excuse me. The y-axis also bounds the region, the x-axis. I just can't get it right today. Okay, y equals 0 is the x-axis. That also bounds the region. So it's kind of up to you if you're going to take the top half or the bottom half. It doesn't matter. It's the same. Let's just take the top half. This is the region. And we're going to spin it around the x-axis. So when it spins, then it's going to create that little football shape. Okay. We need to draw a typical shell. So this can be tricky for students. When you're drawing shells, look at the axis of revolution. It's a horizontal line that we're spinning around. Yes? So what you do is you draw a little horizontal line segment in the shaded region. Don't go outside of it. Okay, here we go. Little horizontal line segment in the shaded region. Then you reflect it. That's the height of your cylindrical shell. This is h. Always use the original region when determining the height and the radius. And then here, let me just add in the rest of my cylindrical shell. Wow, beautiful. Where's the radius? It's right here, everybody. Good. There's the radius. So let's remember the formula for volume for cylindrical shells. 2 pi, I'll just put a to b, you can call them whatever, RH. And in this case, since we're spinning around the x-axis, we're peeling parallel to the axis of revolution. I'm going to integrate with respect to y. Okay, very good. Now let's determine what r and h are. R, h. Now, when doing cylindrical shells, the radius never involves the functions that bound the region. No, it's different than when you do discs and washers. The radius is going to be plain old x or plain old y, depending on what you're integrating with respect to. Sometimes there's a constant involved if you spin around something other than the x or y axis, but you're never going to have like y squared in there, okay? So the radius, in this case, we're just spinning around x-axis. The radius is y. This is the distance up that the y value is at. So radius is y. Now the height is this piece here, okay? The height, in order to determine how it's defined, we're going to take right minus left endpoints, or where it intersects the region. Who's bounding the height on the right? 8 minus y squared. Who's bounding the height on the left? Y squared. So there you go. The height is 8 minus y squared, which is 8 minus 2y squared. If we had spun the other way and the height was vertically determined or stacked, then you would do top minus bottom, okay? If you need more help, I have so many nice videos on cylindrical shells. Don't you worry. I'm going quickly, I know. Okay, so from here, the only other thing we have to do is figure out our limits of integration. Those depend on the original region before you spun. So some people did mess this up. The original region before we spun, I said you could either pick the top half or the bottom half. We picked the top half. So the limits should go from 0 to 2, not negative 2 to 2. No. All right, let's set her up. Volume is, take the 2 pi out, integral 0 to 2, radius times height, dy. And then from here, you're pretty much like footloose and fancy free because, I mean, this is just a harmless little polynomial. Just distribute, yes, 2 pi, integral 0 to 2, 8y minus 2y cubed dy. And then now we can just go ahead, take the antiderivative, keep the 2 pi outside. This will be 4y squared minus 2 over 4, that's 1/2, y to the 4th, evaluated from 0 to 2. So this is 2 pi times 4 times 4 minus 1/2 times 16 minus 0. What's this? 16 minus 8, so that's 8 times another 2 pi, 16 pi. Okay, I think the biggest issue for students was either they didn't remember the formula for cylindrical shells correctly, and then several of them messed up the limits of integration. So always remember, limits of integration are based on the original region before you spin it. Yes? Good. Okay. Next one, classic one, evaluate the integral 0 to 1 y times tan inverse of y dy. So this is by parts time. Anytime you have an inverse trig function, you're going to let that be u, because we don't know the antiderivatives of inverse trig functions without using integration by parts to compute them. So let's hop to it then. U is going to be tan inverse of y, and dv is y dy. So now let's go ahead and take the derivative du. Derivative of tan inverse of y is 1 over 1 plus y squared dy. And v, antiderivative of y, is just 1/2 y squared. Okay, this one also has limits, so we're going to need to be careful about that. 0 to 1, but we got this. So now, using my biparts formula, I'm going to have uv, which is 1/2 y squared tan inverse of y. This is going to get evaluated from 0 to 1, minus integral 0 to 1 of v du. I'm going to take that 1/2 outside and then write this as y squared over 1 plus y squared dy. Are we okay? Good. Now, when I'm looking at the integral that's left over here, it's a rational function. The degree of the numerator is equal to the degree of the denominator. So before we proceed with any techniques, we need the degree of the denominator to be higher. Like whether you're going to do partial fractions or something else, you want degree of the denominator higher. Well, you can long divide, or you can do a little snazzier trick, okay? And because the numerator is so similar to the denominator, I can just manipulate and add and subtract 1. Oh, that's my alarm. I'm already awake. Didn't they know? I can add 1 and subtract 1. Okay, now what does that let us do? I will show you. It's basically to avoid long division and get the ball rolling. Rewrite everything, okay? So 1/2 integral 0 to 1. And then I'm going to split this up. I'm going to write y squared plus 1 over the denominator. And then I still have minus 1 over that same denominator, yes? Let me color code for you in case you can't see it. This y squared plus 1 is here. And then this minus 1 is right here. Why is that so fabulous? Well, this just gives me now 1. We can take that antiderivative, no big deal. Minus 1 over 1 plus y squared. Oh, I love it. 0 to 1, 1/2. I'm just rewriting everything. I don't like to evaluate this until the very end when I'm evaluating everybody, but some people do it differently, so you just live your life. Just don't make a mistake. Okay, here we go. I'll put a little bracket. 1/2 y squared tan inverse of y minus 1/2 times. Antiderivative of 1 is y. Antiderivative of 1 over 1 plus y squared is tan inverse of y. So I'll put minus tan inverse of y, and this is all getting evaluated now from 0 to 1 all together, okay? Let's distribute that negative 1/2 through before we do this. And if I was, working through, and several of my students, they do multiple steps at once, but I didn't want to skip too many right now for you guys. But, if it's algebra stuff and you don't need to write every tedious little step and you won't make a mistake, I always say go for it. Okay, I'm doing great. Here we go. Upper limit, 1/2 times 1 times tan inverse of 1 is pi over 4 minus 1/2 times 1 plus 1/2 times tan inverse of 1, which is pi over 4, minus 0 plus 0. Okay. So what does this give us? Pi over 8 minus 1/2 plus pi over 8. So that's 2 pi over 8, pi over 4, minus 1/2. All right. If people got something wrong on this problem, it was a few forgot to distribute the negative. That's not a big deal. That's like minus 1/2 at best. And then the other thing was, sadly, they don't know tan inverse of 1 is pi over 4. So get that unit circle under control, or however you remember it. You know what I mean? But pretty much this was a good one. I've made them practice this one a bunch of times, so they showed up ready. Okay, here we go. More integration. Here we have an indefinite integral, this time y squared over 49 minus y squared to the 3/2 dy. Do you know what to do? It's trig sub time. Yes, it is. Okay, notice here, this expression is a constant minus the variable squared. So then we're going to use sine theta. And a is 7. A squared is 49. So I'm going to go ahead and let y equal 7 sine theta. And then dy would be 7 cosine theta d theta. We got it? Good, good, good. Okay, now let's go back, replace everything to be in terms of theta. So that y squared in the numerator is now going to be 7 sine theta squared. This guy, 7 sine theta squared. dy, I'm going to replace with 7 cosine theta d theta. Okay, here it is, minding its business. And then in the denominator, we've got that 49 minus y squared. So that's 49 minus y squared is also 49 sine squared theta. And then this is all to the 3/2 power. This too came out ugly. Let's fix it. Doop. Okay, so now we just got to clean up. In the numerator, let's see, we've got 7 squared sine squared theta times another 7 cosine theta d theta. I'm writing it that way for a reason, you'll see. And then inside those parentheses in the denominator, I can factor out a 49. And then I'm left with 1 minus sine squared theta. And then this is all raised to the 3/2 power, yes? Okay, good. Now check out the numerator. I have altogether 3 sevens. So I'm going to write this as 7 cubed sine squared theta cosine theta d theta. And then in the denominator, this exponent here needs to distribute to everybody inside the parentheses. So that's going to be 49 to the 3/2. And yes, it's time to replace 1 minus sine squared theta with cosine squared theta. So then we're going to have cosine squared theta raised to the 3/2 power. Are we good? Okay. 49 to the 3/2 means you take the square root, that denominator root of 49, and you raise it to the 3rd power. So that would be 7 raised to the 3rd. But oh me, oh my, I have a 7 to the 3rd right here. So then this just cancels out so beautifully. Goodbye. And then over here, again, when you raise something with an exponent to another power, you just multiply these exponents. So 2 times 3/2 just gives me 3. So let's just rewrite all of that in the next line. Now I have sine squared theta cosine theta over cosine cubed theta d theta. Yes? I can cancel out one of the cosines now. Cosine squared. And then I have sine squared over cosine squared. Where'd my squared go? Okay, so now you're thinking, how am I going to evaluate this? What can we do? Well, this is tangent squared theta. Yes, it is. Do we know antiderivative of tangent squared theta? No. But we can use a Pythagorean identity, rewrite tangent squared theta as secant squared theta minus 1, and then now we are in business. What's the antiderivative of secant squared theta? Good, tangent theta. Minus, we're integrating with respect to theta, so antiderivative of 1 is just theta. Plus c. Okay, don't box it just yet. We're not done. I know it feels like a time to celebrate, but I'm sorry, it's not. Remember, the original problem was in terms of y, so we have to go back. How do we do that? We're going to go look at the original substitution we made and draw a triangle. So let's go up, 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 up. Remember, y was 7 sine theta. So what you want to do is isolate the trig function sine theta. Sine theta is equal to y over 7. I'm going to use that to make a triangle. I'll make the triangle down here so we can reference it, okay? So sine of theta is y over 7. Usually this app knows I'm making a triangle. So sine of theta is y over 7. That's the ratio of the opposite over hypotenuse side. I can find the missing side using the Pythagorean theorem. So it's going to be square root 49 minus y squared. And yes, we saw that expression in the original integral. That's not a coincidence. That will happen all the time. So now using my triangle, I can figure out what tangent of theta is going to be. Tangent of theta is ratio of opposite over adjacent side. So that would be y over radical 49 minus y squared minus, and then when you have just plain old theta, you have some options which inverse trig function you would like to use to express it as, but I just say go with the one, and it's not just me, conventionally, you go with the one that you used for the substitution. So I would say theta is sine inverse of y over 7 here, and then plus c. And we're done. And nobody rationalizes this denominator. It's worthless. Okay, how was that one? Yeah, they did fairly well. I think almost everyone got this one right. Okay, here's another. Integral 6x squared plus x plus 80 over x cubed plus 16x dx. Any ideas what to do? Yes, it's time for partial fraction decomposition. Isn't that exciting? And notice this rational expression is already bottom heavy. The degree of the denominator is higher than the degree of the numerator. So let's go ahead, let's find the partial fraction decomposition. Okay. We need to factor the denominator. So we have 6x squared plus x plus 80 in the numerator. And then downstairs, let me take an x out. That's all I can do. And I'm left with x squared plus 16. Now that's prime, right? X squared plus 16. Okay. So here we're going to have x is a linear factor, a over x. X squared plus 16 is an irreducible quadratic. So I need bx plus c up top. And then in the next step, we multiply everybody by the LCD, which is x squared plus 16. So what do we have now? 6x squared plus x plus 80 equals a times x squared plus 16 plus, this is going to be bx squared plus cx. I would keep distributing. Since we have a factor that's an irreducible quadratic, we have to set up a system of equations to solve for a, b, and c. We can't just, well, I guess we could substitute in 0 for x and then substitute in something else. But usually I do it this way. Okay, let's look at all of the coefficients of the terms that involve x squared. So on the left, we have a 6. And then on the right, I have ax squared plus bx squared. So that means 6 has to equal a plus b. Now what about x to the first? We've got a 1. Oop, that's c. Fabulous. I love it when you get like a freebie like that, you know? And then what about the constant terms, or x to the 0? We've got 80 equals 16a. Another freebie. So that means a is 5. And then if a is 5, then I can see b is 1. So we're good. That was pretty straightforward. So now our integral looks like the following. We have a over x, so 5 over x, plus bx plus c is going to be 1x plus 1 over x squared plus 16 dx. And then we do need to separate that second term. So we're going to have 3 separate little baby terms. 5 over x, you know what, let me just break it up into 3 little integrals. 5 over x dx plus x over x squared plus 16 dx plus 1 over x squared plus 16 dx. And we're just going to knock these out one at a time. So I'll number them. 1, 2, 3. First one, 5 over x dx. You should know that. Yes. 5 natural log absolute value of x. And then I'm going to just put plus c1 so we can save the plus c for the grand finale. Number 2, at this point, my Calc 2 class can do this U sub in their head. They were not like that at the beginning of the semester. And I told them they would become like this. I think they looked at me like I was crazy. And then now look at them. I mean, they're machines. But basically, yes, you would let u be x squared plus 16. du is 2x dx. 1/2 du is x dx. And literally, like, they're so good now. They're just like, boom, 1/2 ln. You can switch to parentheses because x squared plus 16 is always positive, plus c2. The third one is a common one that you should just memorize the antiderivative of. Let me add a page in here. If you forget it, you could do a trig sub. That's how, you know, you can also, that's one way to prove it. But it comes up so frequently, it's not worth going through that process. So this one, just recognize we have a 1/4 tan inverse of x over 4 plus c3. So the common form to memorize is when you have 1 over x squared plus a squared dx, it ends up being 1 over a tan inverse x over a plus c. Okay? That's just something to put in the memory bank if it's not there for some reason. So then we can put everything all together. All together. We have 5 natural log. You do need the absolute value on this x plus 1/2 ln x squared plus 16, and then plus 1/4 tan inverse x over 4 plus c, and then I'm going to say where c equals c1 plus c2 plus c3. Okay, so let's just talk, because I know some of my students are watching, about like what was necessary for the problem for full credit. So if you got up to here and you just split it into 3 within one integral, and then you just did all the antiderivatives, that is perfectly fine. Like, I don't expect you to break it up into 1, 2, 3 unless it's the beginning of the semester. So don't feel like you lost points if you didn't drag this process out, okay? If you went from here, you'd have to split this up, obviously, but you didn't have to split it into 3 integrals. No, you don't have to do that. And you literally just hopped right here, which a lot of my students did. That's perfectly fine, 100%, okay? So don't worry about that. I'm just explaining it right now step by step in case someone's using this to review or to brush up, you know, and they don't remember every little detail right now. But don't fret, that's not a problem. Okay, very good. Moving on, a little more tricky topic, not so straightforward, improper integrals. So determine whether the improper integral converges or diverges. Clearly show all steps in computing the limit. So we have an integral from 0 to natural log of 7, x to the negative third times e raised to the 1 over x squared dx. All right, what makes this integral improper? That is important because some people were not able to successfully rewrite it as a limit. What makes it improper is the lower limit of 0. And maybe that's not obvious right away, but if you remember, x to the negative third, that's 1 over x cubed. We also have e raised to the 1 over x squared dx. It's problematic to have 0 as the lower limit, yes? Okay, so then what do? We rewrite this integral as the limit as t approaches the problem child, 0, and it's from the right. And then you replace that lower limit with t. How do I know it's from the right? Well, if you look at the limits of integration, it goes from 0 to natural log of 7. The only way to approach 0 on this interval is from the right, okay? Good, 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 good. Now, from here, we have to see how are we going to evaluate this integral. And it's just going to be a straightforward little u sub. I'm going to let u be 1 over x squared. So let's let u equal 1 over x squared, which I know is also x to the negative second. Then du would be negative 2x to the negative third dx, which I pretty much have, right? We've got 1 over x cubed dx, so I just have to get rid of this negative 2. So negative 1/2 du, if you want to rewrite it as 1 over x cubed dx, so it's staring you right in the face. There you go. Other thing you have to do is change your limits of integration. So currently t and natural log of 7 belong to x. I need to change them to be in terms of u. How do I do that? I go right here and I substitute them in for x. So u of t would be 1 over t squared. Whoop. And then u, left-handed problems, let me tell you. U of natural log of 7 is 1 over natural log of 7 squared. And it's not cute, but whatever, that's what it is, okay? Good. So now let's rewrite our integral all in terms of u's. You still have this limit as t goes to 0 from the right, but now I'm going to go 1 over t squared is my lower limit, 1 over natural log of 7 squared is the upper limit. Instead of 1 over x cubed dx, I have negative 1/2 du. Let's put the du out here. And then we just have times e to the u. Okay, very nice. If you want to get rid of the negative, you can flip the limits of integration. Let's do that. And let's take the 1/2 out. Like, what is he doing there? Just pestering us, honestly. Limit as t goes to 0 from the right. 1/2. Now it's positive. I'm going to flip this. 1 over natural log of 7 squared. 1 over t squared upper limit. And then we've got e to the u du. Voila. We should know that antiderivative, don't we? Yes, it's just e to the u. So harmless. Okay, limit t goes to 0 from the right. 1/2. Now I've taken the antiderivative, so we're switching to brackets. We're going 1 over natural log of 7 squared to 1 over t squared. Now plug in those limits, and then this is where people had a few issues. Limit t goes to 0 from the right. 1/2 times e raised to the 1 over t squared minus e raised to the 1 over natural log of 7 squared. Okay, let's think. T is going to 0. Where's 1 over t squared going? Limit t goes to 0 from the right. Where is 1 over t squared going? If you have a non-zero constant in the numerator and the denominator is shrinking, 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 approaching 0, this whole quantity is blowing up. It's getting big. It's going to infinity. We just have to determine if it's going to positive or negative infinity. T is going to 0 from the right, plus this is squared, so for sure this is going to positive infinity. So the exponent is going to positive infinity. E raised to something getting really, really big is going where? Positive infinity as well. Yes. Minus. No, this doesn't cancel. Even if you tried to write it as e to the natural log of 7 to the negative second, no, nothing. Can't simplify. And I know it's tempting, but you have to keep in mind, log properties are very precise. They're precise. If you have natural log and it's a raised to the b, the exponent is just on the argument, then yes, you can move it to the front. That's b times natural log of a. What you cannot do is if you have natural log of a and that whole thing's raised to the b, stop, don't touch. Otherwise, the math police are going to come snatch you up. Okay? So it's not the time to be creative when you're dealing with natural logs. Don't be like, I'm going to make a new property. I'm so sorry. No. Anyways, it doesn't matter. This is just some constant. It's some number. I don't know what it is, but it's finite. I do know that. And then all of this is being multiplied by a 1/2. So let's think. I've got something that's getting very, very large. I'm subtracting some finite number. It's still getting very, very large. And even if I multiply by a 1/2, it's still very, very large. So this limit is going to positive infinity, which means the improper integral diverges. Okay. What were the most common issues? Not switching the limits of integration. Some people didn't even identify where to take the limit. They didn't understand that you have to remove the discontinuity using a limit. Not really remove it, but rewrite it so that you can evaluate the integral. And then the other issue was just actually evaluating the limit and remembering some of our limit rules from Calc 1. Okay? But overall, good. I have to say that this class was one of the strongest I've ever taught, so they did very, very well. Okay, so in the next problem, it tells us use the ratio test to determine if the series converges or diverges. And we have here the sum from n equals 1 to infinity, 3 times n factorial squared over 2n factorial. So to start off, remember for the ratio test, you take the limit as n goes to infinity of the absolute value of a sub n plus 1 over an. And then you compare the result with 1. If it's less than 1, if that limit comes out to be any number less than 1, it won't be negative because we take absolute value, then the series converges. If it's greater than 1, the series diverges. If it equals 1, the test is inconclusive. Since I told them to use that test, don't worry, it's not going to be inconclusive. So we have the limit n goes to infinity n plus 1, that's going to be 3 times, be careful here, this is n plus 1 factorial, all of that squared, over 2 times n plus 1 factorial. I'll put absolute value for now, but we really don't need them. Nothing's going to be negative, so I'll drop them in a second. And then instead of dividing by n, I'm already going to multiply by the reciprocal. So I'll have 2n factorial up here, and then 3 times n factorial squared in the denominator. Very good. So the key here is simplifying correctly so that you can get the appropriate limit. So we have limit n goes to infinity. Let's just go ahead before things start getting wild and cancel these 3's because they don't need to be there. And then n plus 1 factorial squared. I'm going to break it down slowly. So remember, n plus 1 factorial we can write as n plus 1 times n factorial. And that's as far as I need to break it down because I have n factorial here that's going to cancel. So since this is squared here, then I've got 2 of each of these. Does that make sense? So that means I've got an n plus 1 squared in the numerator and an n factorial squared up there. All right, excellent. Now, the next thing I want you to look at is this 2n plus 1 down here. I have to distribute the 2, so that's 2n plus 2 factorial. How does that break down? So that would be 2n plus 2. What's the next number? One integer smaller, that would be 2n plus 1. Keep going. I'm going to stop right here, 2n factorial, because I see a 2n factorial in the numerator on the other term. So that's as far as I need to break it down. It will cancel at this point. We are oh so happy. And then these guys I don't need to do anything with. These are going to get canceled. So they're fine as is, n factorial squared. Now I can just put parentheses. Nothing was negative. If there was like a negative 1 to the n, negative 1 to the n plus 1, after you take the absolute value, those just become positive ones and they go away as well. Okay, now we get to have a lovely little cancel party. Let's see, let's do it in pink. So n factorial squared, gone. 2n factorial, gone. And that's pretty much it for now. We can cancel something else in just a second. So we have limit as n goes to infinity, n plus 1 squared over, now not everyone caught this, but you can factor a 2 out and make this n plus 1 and then 2n plus 1. If you didn't catch that, it didn't really mess up the final result as long as you followed all your properties correctly, but this n plus 1 now can cancel with one of the n plus 1's in the numerator. See how nice? And then we have the limit as n goes to infinity of n plus 1 over, I still have that 2 down there, so that would be 4n plus 2. And then to take this limit, remember no L'Hopital's rule, no, because we're dealing with terms, right? Not a differentiable function. So numerator is going to infinity, denominator is going to infinity, just divide by n or multiply by 1 over n. So we have limit, n goes to infinity. This is 1 plus 1 over n over 4 plus 2 over n. And then now I can say, all right, this term's going to go to 0 as n gets large. So does 2 over n. And all I'm left with is 1/4. What do I care about 1/4? That it's less than 1, since I did the ratio test. So this tells us that the original sum from n equals 1 to infinity of 3 times n factorial squared over 2n factorial converges by the ratio test. Now, if they didn't write me a nice summary like that, I didn't take any points off this time because usually I require this step. It's just that since I told them to use the ratio test, I let it slide today this time. And also the important thing was that they did state that 1/4 is less than 1. That way I know they know the conclusion of each of the tests, because depending on what test you're using, right, this may or may not be important. We have different conditions if we're doing limit comparison, integral test, etc. So you have to always show that you understand what the conditions and results of the test tell you. Okay, next one. Use the comparison test to determine if the series converges or diverges. And we have here the sum, n equals 1 to infinity, 8 plus 9 cosine n over n cubed. So first you have to think to yourself, do I suspect this series converges or diverges? Because if you're going to use direct comparison test, you have to show the inequality in a specific direction in order for the results to tell you something. So the first thing that's like popping out at me is the fact that there's an n cubed down here. So n cubed, right away I start thinking, okay, when we do comparison test, if I have 1 over n cubed and the sum's going n equals 1 to infinity, that reminds me of a p series, right? And p is equal to 3, which is greater than 1. So this series converges. So most likely this series will converge also, because if you look at what's happening in the numerator, it's nothing, life altering for the terms of the series here. 8, that's a constant, not going to do anything. And then cosine n wiggles around, but it doesn't blow up, right? Or approach infinity. So the numerator's not doing much. This n cubed down here, that's running the show. So I suspect this guy converges as well. But remember, when we use direct comparison, we have to show that the terms of our series are smaller than the terms of some other convergent series. You show a different inequality if you're trying to prove the series is divergent. So you have to be so careful here. Can I say 8 plus 9 cosine n over n cubed is smaller than 1 over n cubed? No, I cannot. I can't say that. Absolutely not. So what can we say? Well, I do know that cosine of n, right, is always less than or equal to 1. It's between -1 and 1, right? But I don't need to bound it. I'm not doing a squeeze theorem. No, I'm just doing comparison test, right? I need to show that these terms are smaller than the terms of some other series. So that means 9 cosine n is less than or equal to 9, right? If I just multiply both sides by 9. And then 8 plus 9 cosine n would be less than or equal to, just add 8, 17, yes? So then if I divide by n cubed, nothing's going to change. So now I've shown that the terms of my series are less than or equal to 17 over n cubed. Well, then you just come back over here and you go, just kidding. I didn't mean 1 over n cubed. I meant 17 over n cubed, which is a multiple of a p series. And we have a theorem that tells us if you have a series and it converges and you multiply by some non-zero constant, then it will still converge. And the same thing is true for a divergent series. So then we're good. We showed the inequality that we need to. These terms are smaller than the terms of some convergent series. I just had to come back and toy with it at the end, you see? And that's it. Like, this was direct comparison. We don't need to take a limit, nothing. You just summarize for the people. So this means the sum, n equals 1 to infinity, 8 plus 9 cosine n over n cubed also converges. By comparison, or some of them put by direct comparison, because that's what our textbook calls it. Okay. Good? Are we feeling okay? Very nice. Okay, next, solve the differential equation. Specify what values any constants can be. So here we have dy dt equals t squared times y minus y plus t squared minus 1. So I meant for them to solve this as a separable differential equation. And most of them did it that way, but a few rearranged it and got it into standard form for a linear differential equation. And it worked out. And it was, I love seeing stuff like that. So I didn't tell them how they had to solve it. It's beautiful when things like that emerge. So I'm going to solve it as a separable one, but just know that it can also be rewritten in standard form for a linear differential equation and solved that way as well. And you'll get the same result. I noticed here on the left-hand side, I have 4 terms, so I'm going to factor by grouping. So we have dy dt equals, I can take a y out from both terms here. Then I'm left with t squared minus 1. And then over here, I'm just going to put 1 parentheses times t squared minus 1. So that everything's grouped. So that now in the next step, I can say, all right, dy dt is equal to t squared minus 1 times y plus 1. And then with a separable differential equation, then you break up the differentials here, dy dt. I'm going to move dt to the other side and move y plus 1 over here. So I have 1 over y plus 1 dy equals t squared minus 1 dt. And then now we can go ahead and integrate both sides. On the left-hand side, we're going to have natural log absolute value y plus 1. And then on the right-hand side, look what a relaxing little integral that is. 1/3 t cubed minus t plus c. So when you solve a separable differential equation, you don't put plus c on both sides. You just usually put it on the right, okay? Now we have to try to isolate y, which we can do in this case. So I'm going to take basically e, raise it to both sides, or you could just think of rewriting this equation in exponential form, same thing. So I'm going to have absolute value of y plus 1 equals e to the 1/3 t cubed minus t. And then I'm going to write this as times e to the c. So remember, if you have a to the x plus y, that's a to the x times a to the y. So that's what I basically did right here. Now in the next step, I'm going to drop the absolute value bars. And what does that mean I have to do? I have to put plus or minus on the right hand side. And then let me put this e to the c in the front, and then I have e to the 1/3 t cubed minus t. Very good. And then last thing I need to do, let's get rid of this 1 that's on the left, and I'm also going to redefine this as a new constant. So I'm going to say y is -1 plus k e to the 1/3 t cubed minus t, where, let's tell the people, k is plus or minus e to the c. And then I did state in the directions, specify what values these constants can take on. So k right now, since it's plus or minus e to the c, it's all positive numbers as well as all negative numbers, right? E to the c is never negative, but if I have plus or minus e to the c, then I have all positive numbers, all negative numbers. The only thing I'm not sure if k can be is 0, because e to the c will never give you 0. Can k be any real number? So I have to check, can k equal 0? If k is equal to 0, then my differential equation solution would just be y equals -1. Does that satisfy the original differential equation? It was dy dt equals t squared y minus y plus t squared minus 1. So let's check if this indeed satisfies the original differential equation. Dy dt, if y is just -1, that would be 0. And then that equals t squared times -1 minus -1 plus t squared minus 1. I should put a question mark. We don't know. Negative t squared plus 1 plus t squared minus 1. Yes, it does. 0 equals 0. So yes, k can equal 0. So then you can add in now k is any real number. Okay. Very good. What happened on the test? Most of them just put k as any real number without checking if k can be 0. I didn't take off if they did that. I know, look at me. I turned soft at the end. But really you should always check that before you make such alarming statements. Okay, good. Next one was a linear differential equation and solve the initial value problem. So I gave them an initial condition. That way they could go ahead and find C. So we have theta squared dy d theta minus 3 theta times y equals theta to the 5th secant theta tan theta. We're told theta is positive and y of pi is 0. We'll use that at the end. So first we have to get it in standard form for a linear differential equation, which means I need to isolate dy d theta. That's the first thing my eyes go to. So I'm going to divide everybody by theta squared. Then we have dy d theta minus 3 over theta y equals theta cubed secant theta tan theta. Now we need to find our integrating factor, and P of theta is -3 over theta. If you forget the negative, oh my God, some of them did, it just messed up the whole problem so badly. So don't forget it. I of theta is going to be e raised to the integral of -3 over theta d theta. So what is that? That's e to the -3 ln absolute value of theta. We don't put plus c here, okay? It always bothers me a little, but it doesn't make a difference, so. Now, this is the nice part. They told me theta is positive, so I don't need these absolute value bars. And then I'm also going to use a log property and move this -3 to be the exponent on theta. So then I have e to the ln, no more absolute value, theta to the -3rd. So this is just theta to the -3rd. Okay, so in the next step, I go back to my differential equation in standard form and I multiply by this integrating factor. So we have dy d theta times theta to the -3rd minus, I already have 3 theta to the -1st, so that would be 3 theta to the -4th altogether times y. And then on the right-hand side, the theta cubed is gone now, right? Oh, that was key. That was key. Because otherwise, oof, oof, oof. Okay, as long as you've gone through the process correctly, the left-hand side should be, always and forever, the derivative with respect to the independent variable of your integrating factor times y. Don't just write that down and take it for granted. I always check, because I've caught some silly mistakes before right at this step. So let's see, we have to do the product rule, right, when we take this derivative. So if I left theta to the -3rd alone, took derivative of y, it would be dy d theta. There we go. Then derivative of theta to the -3rd would be -3 theta to the -4th times y. There we go. So that I know I haven't messed up or anything yet. How fabulous. Then we're going to integrate both sides with respect to theta. And then on the left-hand side, you don't do anything because you have an antiderivative of a derivative. So you're just left with theta to the -3rd times y. Fabulous. Don't put plus c on the left. We only put it on the right. So antiderivative of secant theta tan theta. Very good. Secant theta plus c. Okay. You could solve for c now, or you could get y by itself and then solve for c. It doesn't make any difference in this particular case. So I'll just go ahead and get y by itself. If I divide by theta to the -3rd, that's the same as multiplying by theta to the +3rd, or theta cubed. So y equals theta cubed secant theta plus theta cubed times c. This does not become a new constant. When you have a variable quantity attached to a constant, that's behaving differently. That's not two constants that can be combined together. So be careful. Now, the initial condition that I was given was that y of pi is 0. So let me go ahead and substitute that in. So that means 0 equals pi cubed times secant of pi would be -1 plus theta cubed, that's pi cubed times c. If I move this guy over, then I have pi cubed equals pi cubed times c. So c is 1. And then we're going to put it all together. And then, you know, since they're calling it y of pi equals 0, I should write my final answer as y of theta equals theta cubed secant theta plus theta cubed. If they didn't write y of theta, I didn't take points off though. Don't worry. Okay, very good. Most of them got that one right. We had practiced it in class too. Very nice. Okay, home stretch. Find the length of the curve, and you'll notice the curve is defined parametrically. We have y equals 5 sine t minus 5t cosine t, y equals 5 cosine t plus 5t sine t, and t between 0 and pi over 4. So you do need to remember the arc length formula for parametric curves. It goes from a to b, definite integral of the square root of dx dt squared plus dy dt squared dt. So let's first take our derivatives, dx dt, dy dt, square them, clean it up, and then we'll write out the whole integral, okay? Let's hop to it then. dx dt. So x is 5 sine t minus 5t cosine t. So let's see what we got here. Derivative of 5 sine t, that would be 5 cosine t. I'm noticing I got to do product rule here. So let me put minus and put some parentheses. Especially during a test, like don't try to skip too many steps in your head. That's when things get dangerous. Derivative of 5t is 5. I'll leave cosine t alone. And then derivative of cosine t is negative sine t, and I'm leaving 5t alone. So minus 5t sine t. Good? So then dx dt, you see how the 5 cosine t's are going to cancel? Boom, boom. And then we're left with only a positive 5t sine t. Okay, that's nice. And then let's see, y is 5 cosine t plus 5t sine t. So then dy dt is negative 5 sine t. Product rule again, but because there's no minus sign, I don't need parentheses, right? We're good. Plus, this would be 5 sine t plus 5t cosine t. The 5 sine t and negative 5 sine t cancel, so dy dt is just 5t cosine t. Okay, that looks great. Now let me go ahead, square both of those, add them together, and see what's going to be underneath the radical sign, if I'm happy with it or not. So dx dt squared plus dy dt squared are going to be 25t squared sine squared t plus 25t squared cosine squared t. I love this because if I factor out 25t squared, we're just left with sine squared t plus cosine squared t. Well, what's that? That's just 1, yes. So we only have 25t squared under a radical. Are you kidding me? That's my dream come true. Here we go. Limits of integration are just plain and simple, 0 to pi over 4. Who wrote this problem? They were so kind. So arc length equals integral from 0 to pi over 4 square root of 25t squared dt. Technically, right, when you take square root of 25t squared, it's absolute value of 5t. But look at the limits of integration, 0 to pi over 4, t is positive there. So we don't need the absolute value bars. I would just say something like t is positive on 0 to pi over 4 before I drop them. Okay, so then we have 0 to pi over 4, 5t dt. This is 5 halves t squared from 0 to pi over 4. And then upper limit minus lower limit, I'm just going to be left with 5 halves times pi squared over 16, yes, minus 0. So 5 pi squared over 32. Most of them got this right. If they didn't mention this, I didn't take off. It's good to think about, but because it didn't affect the problem, I didn't feel like being particularly punitive. Okay. I think the biggest issue people had, they took the derivative wrong. And then they had an ugly integral. That can't be helped. You know, I tried my best to give them a very friendly problem. Okay. Last one. Last of the required problems. Find the area of the specified region. You must also include a clearly labeled sketch of the region. Just one leaf is fine. So find the area inside one leaf of the 4-leaved rows. R equals 5 sine 2 theta. So I taught them like a little way to figure out how long it takes for one leaf to get traced out in a polar curve when you have a rose. You just set the equation equal to 0. And then we're solving sine 2 theta equals 0, basically, right? So let's think. Sine is 0 at 0, pi, 2 pi, etc. So 2 theta equals 0 plus pi times k, where k is an integer. And then dividing by 2, theta equals, I don't need that 0, it's not doing anything, pi over 2k. So every pi over 2, the radius goes from 0 back to 0. That's what this is telling me. So a leaf of this rose is traced out every pi over 2. So if we're just doing one leaf, then I already know my limits of integration are going to go 0 to pi over 2. And I'm going to just use those points to draw one. Okay. And I told them they didn't need to do anything like ready for an art competition. Let's just keep it relaxing. So literally just go 0, pi over 4, and pi over 2. And everyone will be happy. So r is 5 sine 2 theta, if you forgot. So at 0, it's 0. At pi over 4, it's 5. And then at pi over 2, it's back to 0. So 0, 0. Pi over 4, it's 5. 1, 2, 3, 4, 5, all the way over here. And then back to 0. And I just give them a lot of leeway about the other points. They don't have a calculator when they take their test, so they can't really plot the rest of the stuff with a lot of accuracy. Okay. There's the one leaf. But I can see here's my limits of integration. And then you do need to remember the formula for area of a polar curve. So it's 1/2 alpha to beta r squared d theta. I mean, typically the 1/2 is written on the inside, but I just tell them always take those constants out. Okay, here we go. So we have 1/2, limits of integration are 0 to pi over 2. And then the radius squared, that would be 5 sine 2 theta squared d theta. So what do we got here? So this is going to be 1/2 integral 0 to pi over 2, 25 sine squared 2 theta d theta. We can take the 25 outside so it can hang out with the 1/2. The 1/2 is like, I'm lonely. Please send somebody out here. 0 to pi over 2. Then we have sine squared 2 theta d theta. So anytime you see sine squared or cosine squared and you're integrating, you should just be like, little math robot, I'm going to use my half angle identity. So we have 25 over 2. Like, don't think, just do. 1/2. 1 minus cosine. Be careful, be careful. You have to double the angle there. So this would be 4 theta d theta. And then you know what? Let's take that 1/2 out too. So it can just be reunited with everybody. 25 over 4. However, I think we're ready to integrate. So let's go. Antiderivative of 1, theta. And then antiderivative of negative cosine 4 theta would be negative 1/4 sine 4 theta. And we're evaluating this from 0 to pi over 2. So let's see, this is 25 over 4 times pi over 2 minus 1/4. This is sine of 4 times pi over 2, so sine of 2 pi, we know that's 0. Minus, if I'm plugging in a 0, 0 plus 1/4 times 0. So all that's left is that pi over 2. 25 over 4 times pi over 2, 25 pi over 8. Beautiful. Yeah, they did fine. I can't even think, what was the issue? Maybe there weren't really issues. And maybe some people messed this up, but not badly. I thought this one was straightforward. Okay, I said those were the end of the required problems. I put some extra credit stuff on there for them. So here we go. Extra credit. Find an equation for the parabola described. No partial credit. That's how the extra credit works in this class on an exam. So why the heck are there conics? Well, you know, we do cover it at the end of the semester again, and it's conic sections like with no calculus. It's conic sections from good old pre-calc revisited. Mostly because after this class, they're going to go into Calc 3, some of them, and then they do need to start graphing three-dimensional versions of conics, you know, like ellipsoids, paraboloids, hyperboloids. So this is probably just to get them refreshed and ready to do that. Although in Calc 3, pretty much everything's centered at the origin. So anyways, I'll stop talking and solve the problem. The vertex is at 5, -1, and the focus is at 6, -1. We were not asked to graph, but it's key in order to figure out which way the parabola is opening and get everything sorted. So I would just do the sloppiest little sketch. This is sloppy for me. So vertex is at 5, -1. This is 5, this is -1. That's the vertex, that's HK. Yes, HK. Focus is at 6, -1. There's the focus. Okay. Already I know the parabola is opening to the right. How do I know that? Because the parabola always wants to eat its focus. Just imagine it's like a little Pac-Man, and it wants to gobble up the focus. Okay, well, that's just the way it's opening. So that's great. If it's opening to the right, then which variable is squared, x or y? Do you know? It's y. Okay, so that means the standard form is going to be y minus k squared equals 4p times x minus h. Some books use a here instead. So I already know h and k, that's cool. I have it right here. P is the distance from the vertex to the focus, which thanks to my snazzy little graph, I can see P is equal to 1, positive 1, because we're opening in the positive direction. So we're pretty much done. Y plus 1 squared equals 4 times 1, that's still 4, times x minus 5. And that's it. They just had to find the equation. Okay, this was extra. Good, good, good. Moving on. Evaluate the integral. We have e to the 5x cosine 3x dx. So this one boomerangs. A good chunk of them got it. How do I know it boomerangs? Because the derivative of e to the 5x is cyclical. It always involves e to the 5x. And then the derivative of cosine 3x is also cyclical. After like 4 iterations, you get back cosine 3x with some constants. So since both are cyclical, this is one of the cases where we're going to do integration by parts twice. And then our original integral will make a reappearance. It will boomerang back in our face. And then we can just solve for it like a variable. So here we go. It does not matter how you choose u and dv when you are dealing with a little boomeranger. Just be consistent in both rounds. So you don't have to follow Lipit or Liate or any of that, which are just guidelines. Don't follow them like hard and fast rules, okay? I'm going to choose u to be e to the 5x. And dv will be then cosine 3x dx. So du, that would be 5e to the 5x dx. And then v would be 1/3 sine 3x. Okay, so my original integral, I'm going to call it I. That is equal to, using our biparts formula, uv. I'm going to write that as 1/3 e to the 5x sine 3x minus integral v du. And I'm already going to just take the 5/3 and put it outside. And then I have e to the 5x sine 3x dx. So it hasn't boomeranged yet. Look here. E to the 5x sine 3x. I started with e to the 5x cosine 3x. One more round and it's going to boomerang. Now this part, it does matter how you choose. Let's do u bar and dv bar. If u was the exponential portion in the first round, it has to be the exponential portion again in the second round. If you switch them, it'll just undo this line of work and you'll end up at the beginning, okay? I learned that through painful trial and error. So u bar is going to be e to the 5x and then dv bar sine 3x dx. So du bar 5e to the 5x dx. And v bar, it'll be, negative 1/3 cosine 3x. Let's keep our wits about us. Like anytime I notice there's a negative, I go, okay, we have to be extra alert right now so we don't screw it up. Rewrite everything. So I is 1/3 e to the 5x sine 3x minus 5/3 times, here we go, u bar v bar. I'll do it in a different color so you can see it very well. Negative 1/3 e to the 5x cosine 3x. And then I'm going to have minus du bar v bar. But see how there's a minus? That's going to make it a plus. 5/3 goes outside. And then we have e to the 5x cosine 3x dx. Good? Great. Has our boomerang come back to us? Why, yes, right here it is. That's I right there. So let's start cleaning up. I equals 1/3 e to the 5x sine 3x plus 5/9 e to the 5x cosine 3x, and then be so careful. So I've got negative 5/3 times positive 5/3. So what is that? Minus 25/9i. I'm replacing this whole integral with I. There's an I here. There's a negative 25/9i here. I'm trying to find I. I want to solve for I. Get it all by itself. So we got to put them on the same side of the equation. So add 25/9i to both sides. So on the left, I currently have 9/9i plus 25/9i is 34/9i equals 1/3 e to the 5x sine 3x plus 5/9 e to the 5x cosine 3x. And then last thing, multiply both sides by 9/34. 9/34. And you're basically done. You could write I equals, if you just want to go back to the original, that's also nice. I didn't care. They did both. So now when I distribute 9/34, this 3 will cancel, right? So I have 3/34 e to the 5x sine 3x plus just 5/34 e to the 5x cosine 3x, and then you just got to remember to add plus c. I was totally fine if they stopped here. Some of them were just feeling it, taking things to the next level, and they went ahead, they factored and cleaned it up a little bit, and it looked beautiful. They took out e to the 5x over 34 and then wrote it as 3 sine 3x plus 5 cosine 3x plus c. Both got you full 5 out of 5 extra credit. Yes. Oh, and a lot of them did this one well, actually. This is one of the best Calc 2 classes I've ever had in a while. So they were stellar. Last extra credit. Okay, number 11. Find the area of the specified region. You must include a labeled graph of the curves and region. No partial credit, 10 points. So find the area inside the circle, r equals a sine theta, and outside the cardioid, r equals a times 1 minus sine theta. So r equals a sine theta is a circle centered on the y-axis whose radius is a divided by 2. And then this cardioid is symmetric with respect to the y-axis, majority of it being below the x-axis. Let's go ahead, let's find the intersection. That's the first step, because once we know the intersection, we can draw a nice graph and determine our limits of integration. So we have a sine theta equals a times 1 minus sine theta. A cancels out, so I just have sine theta equals 1 minus sine theta. So 2 sine theta is 1. That means sine theta is 1/2. Now I'm only looking at solutions from 0 to pi because this circle is sitting centered at the y-axis. Right? So, I mean, I could already graph it. The radius is at a divided by 2, and then this would be a. So notice I don't need any solutions outside of 0 to pi. That's where this entire circle lives. So theta let's see, sine is 1/2 at pi over 6, and then again at 5 pi over 6. So that's where the circle and the cardioid intersect. Okay, and then to graph the cardioid, like I already have the circle taken care of. If you want to make a table, you can. You can do theta and then r, which is a times 1 minus sine theta. And cardioids are always traced out 0 to 2 pi. I would just hit your quadrantial angles. Don't get too carried away. 0, pi over 2, pi, and 3 pi over 2. So let's see. If theta is 0, r is a. If theta is pi over 2, r is 0. If theta is pi, r is a, and then 3 pi over 2, 2a. So let me plot the cardioid. So 0, a, 1, 2, 3. I determined this was a, so that's a. And then pi over 2, 0, pi, a, and then here's the problem. 3 pi over 2, 2a. So I just got to go 1, 2, 3, 4, 5, 6, like a little bit more down there. And they intersect at pi over 6 and 5 pi over 6 here. So just show that. Boop, boop, boop. Boom. Boom. Oh, hold on. That right half is so lumpy. Is that better? No. Okay, at some point we have to move on with our lives, so we'll just take that. Okay, be careful. We want the area inside the circle, outside the cardioid. Inside the circle, but outside the cardioid. So that's right here. Boop, boop, boop. Okay. Very good. So when you're doing polar area between two curves, you'll have 1/2 alpha to beta, and you do r outer squared minus r inner squared d theta. So you have to determine which one's the outer radius, which one's the inner radius. So I'm going to show you something that I do even in Calc 3 that's very useful, especially for polar curves like this. So you want to go ahead, draw a ray that starts at the origin and goes outward, right? Whichever curve it hits first is your inner radius, whichever one it hits second is your outer radius. So let me draw one for you. Like say we go this way. Yeah? It hits the region now. That's our inner radius. And then it hits the other curve, that's my outer radius. If you try it again, from the middle it's hard to see. If you go this way, you can see it a little bit better. Allow me to zoom in. Where it hits first is your inner radius, where it hits second is the outer radius. Okay, so I could see outer radius is the circle, a sine theta. Inner radius is the cardioid, a times 1 minus sine theta. And what are the limits of integration? Pi over 6 to 5 pi over 6. Okay, so let's set this all up. So area equals 1/2 pi over 6 to 5 pi over 6. I have a sine theta squared minus a times 1 minus sine theta squared d theta. Now, I did a few things to make the whole process of integrating easier. Notice this region is symmetric with respect to the y-axis. So I actually doubled it and went from pi over 6 to pi over 2. Why did I do that? Because pi over 2 is easier to evaluate than 5 pi over 6, in my opinion. Okay, and I think if you try it, you'll agree. So let's go ahead and do that. So I have 2 times 1/2. I'll write all that out so you know where everything's coming from. Pi over 6 to pi over 2. And then we're going to have a squared sine squared theta minus a squared times 1 minus 2 sine theta plus sine squared theta d theta. Okay? I can also take this a squared out. And we'll put it in front. It's just a constant. It's not a variable. So we'll have a squared pi over 6 to pi over 2 Now we have sine squared theta minus 1 plus 2 sine theta minus sine squared theta d theta. And then now it's not a bad integral, because see how sine squared theta cancels out? Yep, it does. So you're just left with a squared integral pi over 6 to pi over 2. And should we leave it like that? No, let's write 2 sine theta minus 1. So we have the positive term in the front. Let's put our best foot forward. Okay, I think we can integrate, right? Yes, we can, Professor V. A squared times antiderivative of 2 sine theta would be negative 2 cosine theta. And then this is just minus theta, pi over 6 to pi over 2. Okay, so this is a squared times negative 2 times cosine of pi over 2 is 0, minus pi over 2 minus lower limit, negative 2 times cosine of pi over 6, that's rad 3 over 2, minus pi over 6. Okay, what has happened to us? So we've got a squared times negative pi over 2 plus rad 3 plus pi over 6. Okay, negative pi over 2 is, where did that go? I think I hit undo by accident. This is negative 3 pi over 6 plus pi over 6 would give me negative 2 pi over 6. So a squared times negative 2 pi over 6 is negative pi over 3 plus rad 3. That looks ugly. A squared times rad 3 minus pi over 3. And then what happened? Some of them, I think they got a common denominator. Yeah, I think some, this is fine. Stop here if you wish. I wish to stop. But what did I see? I saw 3 rad 3 minus pi over 3. That was cute. Whatever, something like that. As long as it was correct, I didn't care how far they simplified. So I think the trickiest thing was probably graphing, finding the intersection. The integral itself was not bad. If they made some boo-boo though, I think they ended up with a crazier problem. The best part of this was those sine squareds canceling out, then we didn't have to bust out our half angle identity. So that concludes the final exam. Every single problem though, if you need to review the topics where it comes from, then just check out the Calc 2 video lectures playlist because it's linked in the description. I just went through solving quickly, like this is not how I teach, but I know it's probably helpful for some of you guys to use as review, and my class always likes to see the solutions after. We have summer break for like a wee bit, but then I am teaching again shortly. So I'm gonna work on making new content in the meantime as much as I can. Thanks so much for your support. Give the video a thumbs up, subscribe if you haven't already, and also please follow me on Instagram and TikTok, Twitter, Math with Professor V. I love you all so much, and I'll be back sooner than later. Bye.